So as we have talked about circular motion, we've learned about the some of the basics of circular motion. We've learned about the gravitational force and Newton's law of gravitation. And today in this video, we're going to go ahead and we're going to talk about the motions of planets, and we're going to learn about Kepler's laws of planetary motion. So let's talk a little bit about Kepler's laws, and hopefully this is going to help us be able to describe the orbits of planets. So the story of the laws of planetary motion starts with this guy, this handsome gentleman here. His name is Tycho Brahe. Some people pronounce his name Tycho Brahe. I don't know which one is right. He was a Danish guy, a rich Danish guy. I don't speak Danish, so I don't know which way to pronounce the name is correct. But Tycho, what he would do is he would go out and he would record the positions of the planets in the sky. Like every night that he could go out and do this, he would go out and he would record the positions of the planets in the sky, and he would keep records of that. And he hired him an assistant. By the way, Tycho was known as a party animal. Okay, he lost his nose in a duel. He wore a fake nose. He was a drinker. He was party guy. He hired himself an assistant by the name of Johannes Kepler. Johannes Kepler was a German who came to work for Tycho, and he was his assistant, and they couldn't have been more different. Whereas Tycho was, the party animal, Kepler was, the straight-laced, button-down, give me the numbers and let me do some math kind of guy. Now, he was the real party animal. All right, now, Johannes Kepler spent a lot of his life looking at Tycho's data that he had collected and developing some rules for how planets move. And that's what we're going to talk about here. We're going to talk about Kepler's laws of planetary motion. And there are 3 of them. Now I'm going to tell you what, just kind of my own interesting take on this. Tycho and Kepler, over the course of their lifetimes, probably spent many years collecting data and analyzing it to figure out these rules having to do with the motion of planets. I remember when I was in college, starting with the second law of motion, force equals mass times acceleration, using a little bit of calculus, we in one class derived these 3 laws in about an hour. So, whereas they spent all of that time, Isaac Newton came later with the laws of motion. So using that and calculus, could have saved a couple of lifetimes of work. So, just saying. Let's go ahead and let's talk about some of Kepler's laws of planetary motion. Kepler's first law of planetary motion is often called the law of ellipses. And what it says is that the orbit of a planet, and it doesn't have to be a planet, it could be a satellite, it could be a moon, it could be a whatever is orbiting something else, right? What it says is that those orbits are not circular. They are instead ellipses. They're elliptical orbits, not circular orbits. And so knowing something a little bit about the geometry of an ellipse could be a little bit helpful here, right? So if you take a look, here I've got a piece of paper with 2 push pins in it and a length of string, and I'm going to draw me an ellipse. I'm going to take the string and I'm going to put it over the push pins. I'm going to hold them down, and I'm going to draw like this. And if I were the better artist, it would be a better ellipse, but there you can see I've drawn an ellipse, okay? It's not exactly a circle. What it is it's more of a stretched out circle, okay? And an ellipse, inside of the ellipse, there are 2 points, each point called a focus. See where I have my push pins right here and right here? Each point is called a focus, and the word focus has a weird plural. So if I refer to 2 of them, they're not focuses, they're foci, right? Foci, F-O-C-I. So here's an ellipse, and inside the ellipse there are 2 points that are called the foci. And the orbit of a planet, or really anything else that's in orbit, is an ellipse with the sun at one focus. So if here we had like a planet orbiting the sun is at one focus, and then at the other focus there isn't anything there, right? So this is what the orbit of a planet looks like. Some planets will have very circular orbits. In a very circular orbit, the two foci are close together. So if I were to put my push pins very close together here and draw me an ellipse, this ellipse would be very circular. So you go out like this, go out like this. Bear in mind, I'm not the best artist. Okay, so that ellipse would be a little bit more circular than the one I drew the first time. But still, for the planets in that orbit, the sun would be at one of those two foci, right? If I were to put my push pins further apart, then I draw an orbit, an ellipse, that's much more stretched out. You can see this ellipse is much less circular. Okay, and if I had a planet in an orbit like that, it would still be the sun at one of the two foci. Okay, we have a way of talking about how stretched out the orbit is. Okay, an orbit like this, we say, it's very stretched out, it's very elliptical. An orbit like this one is much more circular, right? What the word that we use to describe how stretched out an orbit is, we use the word eccentricity. Okay, and the eccentricity, it's a number that we can calculate. We're not going to go ahead and calculate it right now, but it's a number you can calculate that's between 0 and 1. So a planet that has an orbit that's closer to 0 will have an orbit that's much more circular. And a planet that has an eccentricity closer to 1 will have an orbit that's much more stretched out and elliptical. I believe that the planet with the lowest eccentricity, that is the most circular, is Venus, is the most circular orbit. And I believe Halley's Comet has an eccentricity of 0.9 something. So that's pretty close to 1, right? So it's a very eccentric orbit. So, planets tend to have very circular orbits. Comets tend to have very eccentric orbits. And asteroids can be somewhere in the middle. So there's a little bit about the first law of planetary motion. Kepler's first law of planetary motion says that the orbits of planets are ellipses with the sun at one focus. One thing you might notice, and I want to clear up because a lot of people notice this and start to think this, and it's not true. You might notice that in an elliptical orbit, there will be times when the planet is closer to the sun and times when the planet is further away from the sun. And a lot of people, when they first learn this, they get into their head that must be the reason for the seasons. They think in their head that when we're closer to the sun, that must be summer, and when we're further from the sun, that must be the winter. Absolutely not true. What you got to keep in mind is that when it's summer here in the northern hemisphere, it's winter down there in the southern hemisphere, and we're both at the same point in Earth's orbit. So, our proximity to the sun is not the reason for the seasons, because we have both seasons going on at the same point in the orbit, depending on which part of the Earth you're on. Instead, the reason for the seasons is the tilt of the Earth, right? In the northern hemisphere summer, we are tilted towards the sun. And at the same time as it's summer here in the southern hemisphere, it's winter, and they're tilted away from the sun. 6 months later, come around to the other side of the sun, the tilt is going the other way. The northern hemisphere is tilted away from the sun, and at that point it is winter for us, and it's summer in the southern hemisphere. We are actually furthest from the sun when it's summer in the northern hemisphere, generally. That point where we're furthest from the sun has a special name. It's called the Aphelion. It's the point furthest from the sun. And then the point closest to the sun also has a special name called the perihelion. If we're talking about an object orbiting Earth instead of the Sun, then we kind of change the name a little bit. The point where it's closest to the Earth is called the perigee instead of perihelion, and the furthest point is called the apogee instead of aphelion. So think about the word perihelion. The helion part comes from Helios, who was the god of the sun, right? So that's where that comes from. And then G is for, Earth. Other planets have other suffixes that go in the word. I don't remember. I used to know what the one for Mars was, but I don't remember what it is anymore. But yeah, this is not the reason for the seasons. The reason for the seasons has to do with Earth's tilt, not its proximity to the sun. Let's talk about Kepler's second law of planetary motion. Okay, you'll see a diagram here, and in this diagram you can see the Earth and that's probably the Earth, I'm assuming, at different points in its orbit around the sun. You can see the sun offset from the center at one focus of the ellipse, and then you can see the position of the Earth at different points in its orbit. Now, the second law of planetary motion is often called the law of equal areas. Okay, you can see it's kind of broken up into kind of triangle-ish shapes there. They're not exactly triangles because one side isn't straight, but in the kind of triangle-ish shapes. Each one of those triangle-ish shapes, some of them are blue and some of them are white, each one of those triangle shapes has an equal area. Okay, and what Kepler's second law of planetary motion says is that a line between a planet and the sun will sweep out equal areas in equal times. So you can see 1 month between each of those lines, and then the interior area there will all be equal for each segment. Okay. Now this has some consequences, some interesting consequences. If you take a look at how this planet moves during the months, look at the distance that it moves between, let's say, July and August. It's a pretty short distance there, right? But then look at the distance it moves between December and January. It's a much bigger distance. So you can see that as that planet approaches perihelion, where it's closest to the sun, it's covering more distance in the same time. So both of these segments are 1 month long, right? So you can see it's covered more distance in the same time, which means it's moving faster. Okay, so as the planet comes towards perihelion, as it's moving closer and closer to the sun, it's going to accelerate. It's going to be moving faster and faster until it reaches that perihelion point where it's closest to the sun. And then it's going to start moving away. And as it starts moving away, it's going to start moving slower and slower. So you can see the distance between January and February is large. February and March is smaller. March to April is even smaller until you get to those summer months over on the other end. And that's where the aphelion is, where it's furthest from the sun. And at that point, the planet will be moving the slowest, right? So as the planet goes around the sun, it's not always going the same speed. Sometimes it goes faster and sometimes it goes slower. Kepler's third law of planetary motion states that the square of a planet's orbital period is proportional to the cube of the planet's semi-major axis. Now, I know this is a statement that's so simple it doesn't require explanation, but let's go ahead and do a little explaining about it. Okay, it talks about the planet's orbital period. And what is the orbital period? It's the time that it takes the planet to move around the sun. Okay, so basically it's how long is that planet's year. For Earth, the orbital period is 1 year, right? For other planets, it's different amounts of time. Now, as we use it, we're going to want it in seconds. So yeah, these are going to be large numbers. There's a lot of seconds in a year, and especially if we're talking about like Neptune that takes 30 years to go around the sun, it's going to be a lot of seconds, right? The other thing that it refers to here is its semi-major axis. The semi-major axis is half the distance across the ellipse, half the distance across its orbit, kind of the longer way, right? And most of the orbits of the planets that we're going to be talking about are nearly circular, so we can kind of assume that this is more like the radius of its orbit. So like kind of the distance between the planet and the sun. It's not exactly accurate, but it's accurate enough for what we're going to be doing. Okay. This idea can lead us to an equation to find the orbital period of any object in a nearly circular orbit, so long as we know how far it is from the sun and the mass of that object at the center. So here is Kepler's third law of planetary motion. It says that the orbital period is equal to the square root of 4 pi squared times the radius cubed divided by g times m. Okay, remember g is 6.673 times 10 to the negative 11th. I've forgotten the units. And then m there is the mass of the object at the center, right? So if we're talking about a planet orbiting the sun, m is the mass of the sun. Notice the mass of the planet is not a part of this equation. It's the mass of the thing that it orbits. Okay, we can take this idea here and we can derive another equation. I'm going to spare you the derivation, and I'm just going to tell you, we can come up with an equation here to find the tangential velocity of the planet. So we can find the velocity of a planet in orbit by taking the square root of g times m divided by r. And again, that's the mass of the thing at the center, the sun, or whatever it's orbiting. Let's have a look at how to use these equations in an example. Okay, our example here says, here we have a color-enhanced image of Venus that was taken by the space probe by the name of Magellan. And it was the first spacecraft to be launched from a space shuttle. Neat. During the spacecraft's fifth orbit around Venus, Magellan traveled at an altitude of 361 kilometers. If the orbit had been circular, what would Magellan's period, its orbital period, and speed have been? Okay, so we're going to need some information here. It tells me that its altitude was 361 kilometers, and we have to be careful here, okay? Because this r number, we talked about this before, has to be the distance of the object from the center of the thing that it's orbiting. So here we have a spacecraft going around Venus. We want the distance between that spacecraft and the center of Venus. Okay, when they talk about altitude, that's generally its distance from the surface of the planet. Okay, so and you might think, oh, maybe it's not that big a deal, right? Maybe it's, here's the planet and here's the orbit of your satellite. But no, that's not how it is at all. Really, orbits tend to be very close to planets. So if here's Venus, the orbit of a spacecraft might be like this. Right, and then there is your 361 kilometers. And then we need to know how far is that so that we can add it to that, so we can find the appropriate radius. And so sometimes what we're going to have to do is we're going to have to look up some information about planets. And here is a handy table where we can look up some things about planets. And we're going to need to know what is the radius of Venus so that we can add it to this to find the appropriate r for our equation. And looking at the table here, I can see Venus, its radius is 6.05 times 10 to the 6th meters. So this here is 6.05 times 10 to the 6 meters. Okay. Note that one was in kilometers. I'm going to want it in meters. So let me just change it right now. Let's say this is 3.61 times 10 to the, let's see, kilo is 10 to the 3rd, and then here I have 2 more places, so that'll be 10 to the 5th meters. Okay, so what is the appropriate r to put into my equation? I'm going to add those two together. Let me get my calculator. And we are going to have 6.05 times 10 to the 6 plus 3.61 times 10 to the 5th. And I get 6.41 times 10 to the, let's see, it should be 10 to the 6. 1, 2, 3, 10 to the 6 meters, and we're going to want that in meters. Okay. What else do we know here? We know G. G is a constant. It's always the same. 6.673 times 10 to the negative 11th. What is it? Newton meter squared per, I don't remember the units. Okay. And then we need to know M, the mass. The mass of the object that this space probe is orbiting. Okay. And that would be the mass of Venus. So let's look back at this table and let's see, do we know what the mass of Venus is? And my table there says it is 4.87 times 10 to the 24. 4.87 times 10 to the 24 kilograms. And you would imagine that a planet would be quite heavy, right? All right, now that we know these numbers, let's put them into our equation and see if we can't figure out what they asked us to find, which was the orbital period of that particular satellite, or that particular space probe. Okay, so T equals the square root of 4 pi squared r cubed. So that's going to be 6.41 times 10 to the 6th cubed divided by G, 6.673 times 10 to the negative 11th times M, 4.87 times 10 to the 24th. That's a lot of numbers. Okay. I can just punch all that straight into my calculator. For some, it might be difficult to put all of this scientific notation into the calculator all at once. You might want to work it out in parts. I, however, am going to just stick it all in my calculator and see what it says. 4 pi squared r cubed divided by 6.673 times 10 to the negative 11 times 4.87 times 10 to the 24. And there, okay, so after punching all of that into my calculator, I got 5.66 times 10 to the third, and it's a time, that'll be in seconds. Okay. Now this might be more convenient to express in minutes, because it's a lot of seconds. So let's see how many minutes that is. There's 60 seconds in a minute, so that would be 94. And 3 significant figures, I'll put 94.3 minutes. So take that space probe about an hour and a half to go around the planet. So not too bad. Okay. The question also asked us to find its orbital speed, right? Its speed. So we want to use that other equation we talked about here to find its speed. So let me erase for some room here. Erase my diagram. Okay. The other equation said that the tangential velocity equals the square root of g times m over r. So now I'm going to erase my work here so I have room to do this. Okay, so if I want to find the tangential velocity, I'm going to take g, which was 6.673 times 10 to the minus 11th, times m, that would be the mass of Venus, which was 4.87 times 10 to the 24th, and I'm going to divide by r, which is 6.41 times 10 to the 6th. Okay, let's see what this comes out to. I got the square root, 6.673 times 10 to the negative 11th times 4.87 times 10 to the 24th divided by 6.41 times 10 to the 6th. That gives me 7,120. I need 3 significant figures. I'll just leave 7,120. And that's its velocity. So we'll call that per second. So there we go. Not too difficult, huh? One last thing I want to talk about here real quick. Sometimes when you're talking to people about, stars and planets, and you throw out numbers like the mass of the Earth, people are sometimes incredulous. And, obviously you can't put the Earth on a scale. So how could we possibly know what the mass of the Earth is? How could we possibly know what the mass of the Sun is? The Sun has a mass of about 2 times 10 to the 30 kilograms. I mean, 10 to the 30 kilograms. It's bigger and heavier than the Earth. How could we possibly know its mass? We couldn't put it on a scale. But this is how we know its mass. This is exactly how we know its mass. This is how astronomers calculate the mass of objects in space if they have something orbiting them, right? Because if that object has something orbiting it, then we can easily time its orbit. We just wait for it to orbit once and see how long it takes, right? And then we can also figure out how far that orbiting object is from the object that it's orbiting, right? And there are ways of doing that. And once you have these two numbers, you can stick them in this equation and figure out what's the mass of the object that it's orbiting around. And this is exactly how astronomers do it. They use this equation, right? So how do we know the mass of the Sun? That's how we know the mass of the Sun. Nobody put it on a scale, but we can calculate it very easily. All right, hopefully that helps us to be able to describe the planet of the orbit of a planet. So until next time, take it easy.